Welcome to my class on MS 543 public MI 543, that is relativity. And in this lecture 1, I'd like to basically introduce the subject to you. So basically the special theory of relativity consists of special theory of relativity and general theory of relativity. So though our syllabus focus is on general theory of relativity, but just for the sake of continuation, we will have special theory of relativity as a precursor to learning general theory of relativity. So a couple of classes will be devoted to the special theory of relativity, and in this entire course we will be having as many as 21 lectures, video lectures, along with 7 to 8 interactive lecture sessions, that is online through Google Meet, and the exam pattern and the test, the way we will have to take the test will be announced from time to time. The marking of the test will also be announced in due course of time. So let us now start relativity, special theory of relativity first. So before going into this, first we have to know what is a law. So physical law, normally we say the physical law. Physical laws. So I may have some experiments, suppose, and I have two sets of data, suppose X sets of data and Y sets of data I have, and then I get some relationship on X and Y, maybe suppose S, F as a function of this kind of relationships I will get a function of this, and this proper form of the function may be found out from the nature of the data by data fitting or something. But the question is this a law? Now can I say this Y follows this structure? Can I say it a law? So in order to qualify for any relationship as a law, what we'll have to do is this law must be observer independent. That means one observer observes this set of data and gets a relationship, and another observer in different state of motion or in different state, if he observes a different set of relationship, maybe another set of observers, he gets some X dash and Y dash, and for the same event, and if he gets some other relationships, this relationship is not same, then we cannot call it a law, because it is that in order to qualify for a physical law to be called as a physical law, this must have to be the same event when any two observers observe, and they should get the same structure. Same structure means same event must be seen as a similar combination rule, and only when we will call it a law. Otherwise we cannot call it a law. So Ohm's law or Newton's laws. So they are this observer independence. Here the basic question is observer. So observer 1 or observer 2, they measure and they should get the same kind of relationship. Like in Newton's law, F, some observer in mass into acceleration. So what he gets is, he measures the acceleration, he measures the mass, and when he multiplies, he gets the force. And that's the relationship we got this. And go to another observer. He observes mass as m dash. He observes acceleration as a dash, and when he multiplies these two, and he gets his force. Yes. So in these two relationships, that means for observer 1, the combination rule is mass into acceleration gives you the force. That's the structure that we find here. And if you go to another observer, he might get acceleration different, he might get force, mass different, but when you multiply there, you'll get the corresponding force in that for that observer. So this combination rule is observer independence. This is the characteristics of a physical law. So in order for any relationship to be qualified as a law, we'll have to get this things. So for this, what we need is basically two observers. two observers will have to observe the same event, and they should get the rules, and they should agree with the combination rules. Their individual quantities might be different. So what we do is, now in order to proceed ahead, what we do, we will take observation on certain minimum amount of data, also it's very simple data, and I will try to see the same thing in another observation and try to get their relationships. And if these two relationships, if they agree, then we say that on the measurement of this particular quantity or event, this is a physical law. This is observer independence will be established. So in order to see those things, what we need to observe the events. So what constitutes an event? So mathematically, if you see, for knowing the event, for the details of the event, I need to know its position, I need to know the time. In order for an event to occur, it will take some time, it will record some time. So that record I need to have, and the location I need to have, and depending on this location and time, we can develop other complex quantities or composite quantities and get finally the relation. We will check into this. So first, what we have to know is the frame of reference. So frame of reference means observer basically. So what is a frame of reference? So let's try to see. Frame of reference. So a frame of reference is basically, number one, constitutes a coordinate system, a 3D coordinate system, 3D coordinate systems, coordinate system which will measure location of any given event. And another two is a clock, basically a clock I need which measures a device which measures the time. We conventionally call it a clock. It's not necessarily our traditional clock. It's a measuring device, time measuring device, and this is to measure or record time. And thirdly, what I need is a reference point, a 0 point on the reference point. A reference point to start the measurement. A reference point. A reference point for location and simply reference and for time. For time also, a particular instant of time should be recorded as, should be labeled as t is equal to 0, and from there we'll be measuring things. So if you have all these things, this is called a frame of reference, or physically this is an observer. So what does an observer do? He basically measures the location and measures the time, and from the location and the time he can find out velocity, acceleration, whatever is needed, other composite quantities. This observer can later on build up. So this is the observer's quality. So physically, if we understand, this is a coordinate system. Coordinate system, I need a 0 for measuring the position, and a clock. Here, there is a clock. So clock measures the time, and the coordinate system measures the location of the point. And this is basically observer. What I can say is, this is the observer. So basically he carries a device for measuring length, a device for measuring time. So basically these are all our creations, our imaginations, but if you see physically, so there is an observer who has with him a meter stick and a clock. With this he can measure any event. So essentially, in order to understand, this is the thing. So what I will do is, so I'll record this as x coordinate, This is y coordinate and this is z coordinate, and given any point at particular point. Suppose here, suppose the point P is there. So what does this observer do is basically he measures its location and time. Suppose the location is x, y and z. This is the measurement of location, and he also measures the time. So these four quantities he needs to measure in order to exactly pinpoint what is the event. So in coordinate system we pinpoint a location, but here in event, in this frame of reference, we pinpoint an event. So we record an event with the help of these four quantities x, y, z and t. So I need also another observer in order to check the same point. So another observer, suppose this is the observer. So this is x, this is y, and this is suppose z. And this observer has also clock. And this observer also observes the same event. And what does he get? For the same point, what he measures is x dash, y dash, and z dash. For the location from the coordinate system, he measures x dash, y dash, z dash, and of course, from his clock, he measures t dash. So according to this observer, these are the locations. This is the time recorded for a given event. Suppose some bomb has blasted or something, so which this observer has observed the location to be this one and time to be this one, and this observer observes the same point, the same event, same in maybe that bomb blast to be x, y, z to the location and t the time. So these are these observers. Normally we give a name. Suppose if observer means friend, so let us call it as friend, and another friend which comes this x this way, this. So I will call it as this friend. So basically what I will need two observers or two frames of reference to record a given event. Now, without complicating the things further, so before we understand very complicated events, so let us try to have two very simple observers. So simple observer means suppose S frame is there and another frame S is a particular case. Another frame S this which was originally coincident with this one. It was here. But at t is equal to 0, it starts moving along x direction. This observer, this new observer, and after a time t, he reaches here. And this is S dash frame. So along this is x dash, this is y dash, and this is z dash. So this is after a time t, it goes to distance. This distance is v is the uniform velocity. So what is our assumption? So originally there was a frame S dash and S coincident together, and at t is equal to 0, this S dash frame starts moving along same x direction. It could be y direction or it could be z direction also, but for simplicity let us take it is moving along x direction, and after a time t it has already moved by a distance of vt, and these two observers at that instant t it records a particular event. So this observer similarly records x, y, z and t, and this observer records x, z, y, z and t. And this type of frames of reference where one frame is there and another frame is moving uniformly with uniform velocity along a given direction are called Galilean frames. So these are Galilean frames of reference. Galilean frames of reference. So here what we are discussing is, so how does the situation look when we have two Galilean observers, two Galilean frames of reference when they observe the same thing. And from the geometry, what we can do? In this, if you just look at this, so what is axis? Axis means from here, the word is from here, it moves along this direction by x amount and along y direction by y amount and z by z amount, and the time recorded by his clock here for a given event here to be t dash. So these are the coordinates. And for this is x, this is y, and this is z. Some z that maybe this and this. So z. So he records as x, y, z. And from the geometry we can find the relationship. If you just look at the geometry, then I can directly write x dash is equal to x minus bt. Just look at it, because this is x dash and this is x. So x dash is equal to x minus bt. And if you look at the y component, so y dash is equal to y, z dash is equal to z, and t dash. And it's our common experience that the day-to-day experience that if an event has occurred at a given time, say exactly at 1 p.m., suppose some bomb has blasted here exactly at 1 p.m., then this fellow says that it has occurred at x, y, z and at 1 p.m., and this fellow says that it has occurred at x dash, y dash, z dash, but also at 1 p.m. In time they do not disagree. So this is our common experience. So I can write t dash equal to t, and this is called the transformation law. That means given a set of quantities x, y, z and t from one coordinate system, I don't need to physically go here and measure what should be seen by this observer. With the help of these transformation laws, I can calculate these things. So these are called the Galilean transformation laws. Galilean transformation, not laws actually, transformation relation for position. So for position, if you measure certain event from there, and here you don't need to go, you can directly predict with the help of this data. And if you know the nature of the frame, S frame, that it is moving along this direction, if you know that with the velocity also you know, then I can directly write this, and this is the Galilean transformation for position. The other way around is also true. That means suppose this set of data is available with us. I want to create this set of data. That means I want to have a transformation by using the data from the S frame. I should be able to reproduce what should be seen by this observer. That relationship should be available. And from here also we can directly calculate. I'll write x is equal to x dash plus vt, t is equal to t dash, so I can write like this, y is equal to y dash, z is equal to z dash, and t is equal to t dash. And these are exactly the reverse formula. So these are called the inverse Galilean transformation for position. So these are inverse Galilean transformation for position. So for position or the location, I can directly use this. So these are very simplistic nature frames of reference in which we can find out this transformation formula. Now, nature does not only measure the location and time, it also measures velocity in various events. So it evolves in time, so it has a velocity. So as an example, let us take, suppose this point P is moving with a certain velocity u along a given direction. Vector direction suppose. Is moving, and these two observers are there with the same conditions. Originally they were coincident, and now it is moving with uniform velocity v, and now they want to record, they want to see the velocity from these two frames. And how should I? So let us try to understand how should one measure the velocity. So for velocity, what this fellow will do? This fellow will first try to measure a slight amount of displacement in the x, and he will record the elapse of time in traversing a small path delta x or something, the infinitesimal path delta x, and he divides. So this time is recorded by this observer with his own frame clock. So what he does is he basically measures a small distance x divided by small time elapsed to t. That means small infinitesimal distance delta x and divided by infinitesimal time delta t, and when you divide it, you get the x component of the velocity for this motion as measured in this motion. Similarly, for the y component of the velocity, what does he do is he considers a small infinitesimal amount along y direction and measured by divided by this small elapse of time delta t, and he divides it, he'll get the y component velocity and similarly the z component velocity. And this S frame observer, what does he do? He does the same thing. Of course, he's from his own frame. What he does, from here, he will measure a small amount delta x dash and small amount of time delta t dash from here, and he divides and he gets a u, that means x component of this velocity in his frame. Similarly, y and z component of the velocity. So geometrically, or just using this small relationship, I can directly find out the velocity. So velocity is nothing but the time derivative of x coordinates, coordinates. So we have these coordinates here available, so we can utilize those and try to see what are the different components of velocities in two frames. So let us do that. So now this is Galilean transformation for velocity. This time I will do it for velocity. So here what I will do first, let us consider this one. So we know in the Galilean transformation this is true. So what I will try to do in order to get the x component of the velocity in the S frame, I will try to find the derivative of x dash with respect to t dash, which I will call it ux dash. That means the velocity, x component of the velocity in the S dash frame will be like this. So how to find out? This is nothing but, since I have done this, dx dt dash minus v dt dash. Why v comes out? Because v is uniform velocity, is constant velocity. So as time elapses, this velocity is not going to change. So it's a constant with respect to time. So it comes out. So let's try to see what is this. So there is an x component of the small infinitesimal distance in as measured by this one, but the time as measured by this one. So this cannot form a velocity. So you take small elapse of infinitesimal distance from one frame and time from the another frame. This is not allowed. So this observer cannot mix these two things. So he will use his own this. So we have to transform this t dash to t. And I know from the Galilean transformation t dash is equal to t. So directly I can write this is equal to dx dt. And since t dash is this is t dash. So since t is equal to t dash, this gives you 1. So this is this. And what is this? This is dx dt is the x component of the velocity as measured by S frame. So this is, I will write ux minus v. So what I get is ux dash is equal to ux minus v. So this is the Galilean transformation of velocity for the x components. So let us see for the y components. and z components. So for y components, this result I will keep it somewhere. Ux dash is equal to ux minus v. Okay. Now let us go for Gaussian transformation velocity in the y direction. So as you know, for the y component of transformation, I write like this y. So uy dash is equal to dt dash is equal to, so since I have found out derivative here, so dt dash y, which is equal to dy by dt, which is nothing but uy as measured by the s plane. So what I find is y component of velocity will not change, and similarly for u z dash is equal to dt dash z dash is equal to z dash is equal to z. So z, this t dash is equal to t, directly I will write, and this is u z. So y component and z component will not get. So y component is equal to y, z component is equal to uz. So these are the velocity transformation laws, transformation relationships. So Galilean transformation for velocity will be given like this one. And similarly, just as earlier case, we can also find out the inverse transformation laws for velocities. So while the Galilean transformation laws for velocities are given by ux dash is equal to ux minus v and uy dash is equal to uy and uz dash is equal to uz. These are the Galilean transformation for velocity. So inverse Galilean transformation for velocities are given by just the inverse ux is equal to ux dash plus v, ux dash plus v, uy is equal to uy dash, uz is equal to uz dash. So here what we get, if I am given the components of the velocities in the s frame, I can easily calculate out the components of the velocities as seen by the observer in the s dash frame. And this says that if the data are given in the s direction, s frame of reference, then we can calculate the results as seen in the s frame. So these are the transformation laws for velocities. So here you must have observed one thing. In order to go from the normal transformation to inverse transformation, what we have to do? Well, just is a simple rule. So you make dash quantities to undashed quantities, dash quantities, and wherever there is v, you replace it by minus v. So that will do that inverse transformation. You can easily write it. So dash to undashed, undashed to dash, and this v, which is the movement. So that movement, the transfer velocity. That means you are trying to measure from with respect to this. Actually, what is happening with respect to this appears to be moving in the opposite direction. So you have to you get the velocity v as the reverse velocity. So as seen from this one. So what we find is when you observe a point, these two observers, when they observe an event, the observers will not agree in the positions, because these two observers will record different positions while they agree on the time. Of course, that is, they agree on the time. The y component and z component of positions are also agreeable. Only x component, because it is moving along x direction, so it will not affect any locations here. in y and z axis. So y component, while this kind of observers, they will agree on the y component of the position, z component of the position and the time, but they will disagree on the x component of the position, location. But you come to the velocity, so while this y component and z component of the velocities are agreeable to both the observers, but x component of the observer, the results of the x component of the velocity will not be agreeable to both of them. They will not agree on these two because they are related by this relation. There is a difference measured by p. And in practice also it is happening. Suppose you are standing by the side of the road and you are observing some event, some movement, say movement of what should I say? Suppose a bus is moving and an observer is there, and for this observer, a person in the bus has a certain velocity, measures the velocity. Okay? And there is another bus coming who is trying to overtake this original bus, and there is also one observer. So that is a moving observer, and to him the velocity of the first bus is not same as the velocity as measured by this observer standing by the road. There is a difference in the velocity. So that difference gets reflected in this relationship. So Galilean velocity transformation is this. So let us come to acceleration part. So Galilean transformation for acceleration. Acceleration. Same structure. This time, this particle, this point is accelerating. And while accelerating, some record we have to, some instant we have to record here at a given instant, or this should be at a given event. Some event has to be recorded while this particle is moving. So what is their acceleration is to be measured by, what is the acceleration of this particle is to be measured by these two objects. So just as earlier, I write ux dash is equal to ux minus v. So in order to get x component of the acceleration in the s dash frame, what I will do is the x component of the acceleration in the s dash frame is equal to, it is the x component of the velocity in the s dash frame divided by the elapse of time from s dash frame. So essentially mathematically what I have done is I have found out the a derivative of this quantity with respect to t dash. So here also I have to do the same thing. d ux dt dash minus dv dt dash. Now as said earlier, this is a quantity as measured by s frame and this is a quantity as measured by s dash frame. They cannot be combined this way. So I have to transform this to the appropriate quantity. So t dash is equal to t. I'll write this dux. Similarly here also I will do this dv dt. So this is nothing but x component of the acceleration in the s frame, and what is this value? This value is 0 because this velocity is uniform. So it's uniformly moving as this frame with respect to s frame. So this velocity is 0. So this is minus 0, which is ax, and this side it is ax. So x component of the acceleration is agreeable to both the observers. So let us go to y component of the acceleration. So this also will record here. Ax dash is equal to ax. Now come to y component. It's very easy. Y component, earlier we got this is y. So in the similar elements, so this is y dash is equal to a y, and from this relationship z will get a z dash is equal to a z. So what we find is a y dash is equal to a y and a z dash is equal to a z. A z. So what we get is the Galilean transformation. So when you when there are two observers, one moving with respect to other with a uniform velocity, the results can be differing in this fashion. So we find this acceleration is not changing. While these two frames will disagree on their positions, positional records, velocity records, but they are agreeing to the results as measured by their individuals. This acceleration, they are agreeing to the acceleration components. So if the acceleration components are same in both the frames, then the Newton's law, what does it say? By this time we have already said Newton's laws, but we know this one. But before we say it in law, so what we see? So Newton's law is m into a. M into a. Suppose it is measured by some experiment. This observer wants to verify this particular law as given by the Newton. So what he gets is he gets an a for a given movement of the particle. So he gets a, and he multiplies this m, the mass of the particle, and he gets force. Okay, and this fellow, another fellow, this S dash frame observer, he measures S dash, and mass is not from our usual experience. Mass doesn't vary with the observer. So m dash is equal to ma, and when you multiply, you get this force and both the things are agreeing. That means this Newton's law is observer independent. So from here, since these are identical, these two are also identical, this combination rule is valid in both frames. That means Newton's laws are Newton's laws, we can say, with respect to the Galilean transformations. We have not gone to any other transformation. We have not taken any other frame, the observers, which is accelerating or which is a rotating observer with respect to one another. We have not yet taken. We have just taken very simple. One observer is there, another observer is uniformly moving. In that case, we find that these two laws, the observers, at least this universality, the observer independence, is followed by Newton's laws. So far as Galilean transformation is concerned, we will say the Newton's laws here. But actually, in general relativity of relativity, later we will find that Newton's law is actually invariant or the covariant is for the covariant. The form invariant is for the covariant. This covariance can also be seen in the accelerated frame. So that is for later. So right now we find this Newton's laws. So at that time when Newton's laws and principle of relativity was there, so principle of relativity observer independence is the laws of nature must be observer independent or the frame independent, observer independent. This statement, observer independent. So this statement is seen, the laws of nature. What do you mean by laws? Laws of nature. At that time, when Newton's laws were there, so all the natural phenomena could be explained with the help of Newton's law. So once these Newton's laws are invariant, so you can directly say the laws of nature. So all laws of nature, it's basically dynamical laws. So dynamical things are there. So people say laws of nature, or later into the term of physical laws. Physical laws must be or are observer independent or the covariant. The laws are covariant. So at that time, physical laws means only Newton's law, dynamical law, and that defined the whole physics. But later, electricity and development, the optics was already there, but it was considered to be a different branch. So when electricity and magnetism comes, the whole formula of electricity and magnetism could be concisely written in four with concise formulas, which are called Maxwell's equations, called Maxwell's equations. Maxwell's equations. There are four formulas here. I have not write here. The four Maxwell's formula, four equations will give you all electricity and magnetism. And when you play around with it, it was found that this Maxwell's equation, the whole phenomena of electricity and magnetism, also admits a wave solution. These equations will be solved, so you'll get that there can exist a wave, and that wave velocity is given by this. So this is the permittivity, electrical permittivity of vacuum, and this is magnetic permeability of vacuum. And when you get this, and these values are there available, and this velocity is defined by this formula. And when you find out its velocity, this is nothing but 8 meter per second. And this is exactly the velocity of light. So that means light and the equation, wave equation that is admitted by Maxwell's equation could probably be the same. So then light is a form of electromagnetic wave. That was the first suspect, and then slowly other experiments were also there. These equations were played much more, so that all the laws of optics could be derived, and whole lot of optics could be derived with the help of these four equations. And that means if these equations are correct, whole lot of optics is also correct. Since optics has already proved so many diffraction, polarization, interference, everything could be derived equations, so that these equations are correct. If these equations are correct, so one of these results is also correct. Is a velocity as measured by an observer is this constant. But at the same time, for measuring the dynamic, so whether this Maxwell's laws or called electromagnetism is under physical laws. So physical world, this physical world, we have already stated as a principle of relativity that all physical laws must be observable independently. These physical laws earlier included only dynamics. Now people wanted, maybe this is also correct, everything is correct, this is also physical law. So if I put here, then does it follow the Galilean transformation law? Because Newton's law follows the Galilean transformation law. So people try to prove it. If it is so, then if your Maxwell's equation and correspondingly C follows the Galilean transformation law, by Galilean transformation law says that if you measure the velocity, certain component of the velocity in a by S observer as some value, and if the same experiment is done, or if same measurement is done by a moving observer, then there should be differing either velocity. That means if a moving observer measures a velocity c dash and another observer measures this, so it must be related like this. Or if they are approaching together, then c dash could be c plus v. So this means what? This velocity of light must be observer dependent. These two observers will be measuring two different velocities. So that means velocity cannot be constant. But Maxwell's law says that velocity has to be constant. Because here there is no mention of any observer, so this, with respect to any observer, this velocity is bound to be constant as per the Maxwell equations or the laws of electromagnetism, the electrodynamics. The theory of electrodynamics says that velocity of light should be constant all throughout for all observers. But if you want to accommodate this into the principle of relativity, then one has to follow the Galilean transformation, and this Galilean transformation, according to Galilean transformation, should be relative velocity. The velocity of light must be relative with respect relative to the observers. So this was the conflict. It started prior to Einstein. Some people say maybe some automatic changes are there so that this velocity could be same in both the frames. But physically, when it was measured, it was found that the velocity was same in all the frames of reference. So Michelson's model, the famous Michelson model experiment in 1888 directly proved that there cannot be any relative velocity for the measurement of it. So that is, this is correct. Next question is, if this is correct, then are these laws wrong? So now people are in confusion. So whether these set of laws are correct, which are Galilean transformation, which are well obeyed by your Newton's laws, and with the help of Newton's law, so many developments have been made. So this cannot be wrong. This must be wrong. But here, all laws of optics could be found out, were exactly found out. All experiments, polarization, interference, all the ray optics, everything could be found out from the Maxwell equations. And this is one of the outcomes of Maxwell. So Maxwell's equation, since this cannot be wrong, this cannot be wrong. So there was a conflict, and this conflict was first resolved by Albert Einstein in 1909. What has he said? He gives us two postulates. He postulates that laws of physics or physical laws, physical laws are observer independent or the covariant, observer invariant in Galilean frames of reference. Okay, and these Galilean frames of reference are also called inertial frames of reference. In inertial frames of reference. Why inertial? Because the laws of inertia, these Newton's laws, are independent. So these are called inertial frames of reference. So inertial frames of reference. So this time, in this physical laws, he includes Maxwell's equation. That means electromagnetic theory. That means this is true. So it is apparent that this kind of thing is true. This kind of transformation is true. And also he said, to velocity of light is constant in all inertial observers. So the speed of light, is constant for all inertial observers. As we have already said, these two things cannot fit into a single Galilean transformation formula like this. So what did he do was, the revolutionary thing that he did was, he changed the nature of the transformation. He says that this kind of transformation will not be valid. It is the transformation law saying we have to change this, we have to go to a new, so after experiment, after mathematical experiments, he found that these are not the Galilean transformation formula. What you need is low range transformation formula. There's a new set of transformation, low range transformation. So he has directly changed this transformation formula. So something is, these are not wrong, but something is incomplete. It doesn't cover up the entire thing, so entire physics. So it is giving you the right result only for the dynamical, the objects in the dynamical worlds. And later we find that this dynamical, the objects in the later, they move with a velocity much smaller than the velocity of light. So this thing should be valid. But if you want to complete it, so one has to go to the low range transformation. And this is a very interesting point. It says, earlier what we find in the transformation formulas, the location t dash is into t. It was a parameter. Okay? T dash is. The x changes, y changes, z changes, but t doesn't change. T doesn't. But here in the Lorentz transformation formula, it is the even the t acts like your other coordinates. So with the frames, the time coordinate is also changing with time. So the new transformation formula, Lorentz transformation formula, let's go to now Lorentz transformation formula. Lorentz transformation will not derive this, rather ask you to derive it. It's available in the books. If you just consult any book or any note in the internet, then you will find this Lorentz derivation of Lorentz transformation. So I leave it to you. Lorentz transformation. So what is this? Very interesting transformation. X dash is equal to, this is x minus vt but divided by, so this was there already, this thing has newly come. This y dash is equal to y, z dash is equal to z, and t dash is equal to t minus vx by c square root over 1 minus v square by 6. So this is the revolutionary change, just coming from Galilean transformation to Lorentz transformation. Took almost 100 years, not 100 years, it was less than 100 years. It was after the Maxwell equations, all those things came. It took 1864 was the Maxwell's law. If you consider after that, then 1905 is 36 plus 41 years. So after 41 years, these new set of transformation laws, transformation formula were given. In fact, Lorentz gave this transformation earlier in context, but then it was directly used here, the Lorentz transformation formula, to exactly describe, to exactly accommodate both the postulates of Einstein. That is, the physical laws are invariant under all inertial transformation, just as here this one, and at the same time the Maxwell is also correct. So that means velocity of light is constant in all inertial frames. So in order to do this, we have to change this, and we can see that it can be, this accommodates both the things. So these are, so what we understand here is time is also varying with the observer. Earlier the time didn't vary with it. This is the major change that has come. These are only certain modifications. So this multiplied by something. This is same, but the major change is this: the time cannot be the same for both the observers. That means measurement of time are different for two different observers. So that means again, whatever is 1 second, the chunk of time which you define as was 1 second is not the same chunk of time that is for different observers. So from frame to frame, the chunk of time that you define to be 1 second is different. So as a result, this time recording will also be different in different frames of reference or for the different observers. So that's a major change. And we have certain consequences of this. So minimum consequences that you have already learned is, one is length contraction, another is time dilation, another is variation of mass with time, variation of mass with velocity rather, and another mass energy equivalence. These are the four very outstanding results. Equivalence. So basically all these transformations stem from one very basic thing, is that the relativity of simultaneity. What is this? So let us define this relativity of simultaneity. So what has happened that the two events as measured by two observers earlier in Galilean transformation, what happened? In Galilean laws of transformation, what happened? They will not agree to the position, but they will agree to the time. That means if you say that bomb blast is exactly at 1 p.m., this fellow also says yes, it was exactly at 1 p.m. But this fellow says this bomb blast occurred here. This fellow doesn't agree. No, it doesn't occur there. It occurs here. So for them the position was different, but the time was agreeable. But this time, if you see, this time will also not be agreeable. So time is not agreeable means this fellow says this event happened at such and such place, such and such time, and this fellow says such and such place and such and such, and both will not agree. So this time, so immediate consequence from here again. Suppose there are two events occurring here and here, suppose, very nearby, and they have simultaneous. So suppose the two boom blasts were there simultaneous, exactly same with respect to this frame. He says that these events occurred simultaneously. Exactly, there is no time gap. But this fellow says no, there is a time gap between this. So that's why you have to forget simultaneity. Simultaneity is not absolute. Earlier what happened? Your time recording was simultaneity was not affected. If two events occurring at the same time, this observer will also say same, that observer will also say these two events occurred at the same time, at the same instant. Okay, but here in the low range transformation, the simultaneity is not absolute. It is not true for all observers. So it's not absolute. It's relative. Relative means it depends on observer. So observer dependent simultaneity has come. So two events which are simultaneous to an observer may not be simultaneous to the another observers, and it immediately affects the very measurement process. Let's see how, and then we'll wind up for today. The relativity of simultaneity directly affects the measurement process. Relativity of simultaneity affects measurements. We'll try to see how. So let us go to the basic principle of measurements. So how do we measure it? Suppose there is a length and there is one observer. What does he do? He tries to get a coordinate from here. This information has to come to him, and he tries to get this information here, and then he uses these coordinates to find out the distance. So basically it depends on the coordinates, arrival of this coordinate information to these eyes. So long as this is constant, this is stationary, it is not moving, then what happens? This information, suppose it comes now, and this information comes after maybe 10 minutes, it will not affect, because this point is always this point. So this point. So suppose this is moving. Then what happens? Originally it was stationary, he was measuring this distance with this one. Now this is moving, what happens? This point goes here, this point goes here. So by the time this information comes here, this information will not reach, another information will reach here, and this measurement has to be simultaneous. If these two points simultaneous measurements, so if these two events are not simultaneous, then this event and this event will not be simultaneous, and in that case I cannot measure the length. So for the basic principle for measuring the length is the information from these two must be simultaneously reaching the eyes of the observer, and that doesn't happen because once it moves, so by the time this information comes here, the actual information will not come, some other points information will come, and the observer considers that that is the end point because he gets simultaneity there, and he declares that this is the length. So moving lengths are going to be short. Similarly, the time measurements, the time gap between any two events, if you measure the measured by the moving observer will be different than this, and hence because of this relativity of simultaneity and the measurement process, the entire consequences, the series of consequences come: length contraction, time dilation, variation of mass with velocities, and finally it was found that if it is so, then mass and energy cannot be separate entities. These are to be same entity. So these are some of the consequences. We will not be going into each other. We will rather focus on the geometrical representation of the entire these changes, these consequences. So we'll try to understand the special theory of relativity in terms of geometrical representation, which is called Minkowski space. So next we'll go to the Minkowski space in order to understand the details, the mathematical structure of relativity, and then from there we'll try to generalize those points to go to the general theory of relativity. Till then, bye.